Welcome to the AURIGRAVIS Hybrid Lenticular Aerospace Craft Series, a journey through 12 generations of advanced aerospace innovation. This project, credited to Colonel James Edward Hartman, explores the evolution of a compact, modular, and gravetic diamagnetic propulsion system. Each generation builds upon the last, integrating new scientific theories, materials, and control systems to push the boundaries of flight. From foundational diamagnetism to quantum diagnostics, and from environmental coupling to autonomous intelligence, this series offers a comprehensive look at the future of aerospace technology. Let's embark on this archival-grade exploration of hybrid propulsion and field manipulation. Narration 1 lays the groundwork with diamagnetism as the core principle. The lenticular shell is embedded with diamagnetic materials, and energy flow arrows illustrate how field gradients create repulsive lift. Scientific theory blocks beneath the cutaway detail how quantum-coupled composites like Ni at Ni-O/Argo are tested for lift response, establishing a baseline force measurable at 1026 N per unit volume. The postulation is clear. Architectural anisotropy and gradient control can amplify diamagnetic lift far beyond what chemistry alone can achieve. This foundational phase sets the stage for all subsequent innovations in the AURIGRAVIS series. Narration 2 introduces composite amplification and shell integration. The lenticular hull is now layered with advanced materials: core shell Ni at Ni-O/Argo composites, transition metal halide lattices, and magnetoelastic metacomposites. Magnetic dusted mixtures sculpt localized gradient landscapes, and energy flow arrows show how microstructural alignment and susceptibility modulation amplify diamagnetic lift. The scientific block highlights tunable electromagnetic losses, anisotropy modulation, and the avoidance of ferromagnetic locking. The goal is clear: achieve over 10 times the baseline diamagnetic lift, enabling stable levitation and precise directional control. Generation 3, the focus shifts to hybrid gravetic propulsion. The craft's shell integrates PAIS-style asymmetric capacitor arrays, cryogenic shielding chambers, and gravetic coupling modules. High-voltage asymmetry across dielectric layers creates directional field gradients, hypothesized to open gravetic coupling channels. Cryogenic isolation ensures quantum stability and suppresses ion-wind artifacts. Scientific theory block contrasts historical electrogravitics with modern null protocols, emphasizing reproducibility and artifact elimination. Isotopic doping is postulated to influence local gravitational coupling, with quantitative targets set for voltage, field gradients, and displacement sensitivity. Narration 4 explores quantum diagnostics with dual-mass interferometry and entangled mass arrays. Inside the shell, laser interferometers and quantum coherence monitors track phase shifts and displacement under gravetic field modulation. The scientific block details protocols for null field baselines, field modulation sweeps, and isotopic mass channeling. The goal is to detect quantum mismatch as a gravetic signature, with sub-nanometer sensitivity and over 99.9% entanglement fidelity. This phase aims to reveal non-local gravetic coupling beyond electrostatic influences, using rigorous, falsifiable experimental criteria. Narration 5 marks the transition to environmental coupling and field propulsion diagnostics. The craft is surrounded by external field probes, environmental sensors, and ground-based tracking stations. These systems map real-time field gradients, detect atmospheric ionization, and validate propulsion effects without mechanical thrust. The scientific theory block covers field mapping, gravimetric anomaly detection, and adaptive feedback loops. The aim is to confirm shockless displacement and mass-field interaction, with high-resolution diagnostics ensuring that propulsion is validated independently of onboard telemetry. Narration 6 introduces atmospheric field shaping and adaptive lift control. Perimeter field emitters and plasma boundary layers generate controlled gradients and lift bubbles around the craft. Real-time sensors feed atmospheric data into onboard AI, which dynamically modulates field output for optimal lift and stability. The scientific block discusses plasma drag reduction, weather-adaptive algorithms, and ion-wind suppression protocols. The goal is to achieve non-aerodynamic lift and smooth transitions between hover, ascent, and lateral motion, even in turbulent conditions. Narration 7 focuses on internal efficiency with energy recycling, capacitor recovery, and advanced thermal management. The translucent cutaway reveals bidirectional capacitor arrays, cryogenic flow channels, and phase-change heat sinks. Energy is harvested during field collapse and recycled, while dielectric reconditioning and air-controlled cooling cycles extend capacitor lifespan. The scientific block highlights over 70% energy recovery, rapid cooling response, and quantum-stable thermal regulation. This phase ensures the craft's longevity and operational reliability under high-voltage gravetic operations. Narration 8 transforms the shell into a resonant amplifier and stealth suppressor. Toroidal harmonic nodes and multilayered composites reinforce specific field frequencies, amplifying internal fields via constructive interference. Counterphase acoustic emitters and damping membranes cancel out sonic signatures, achieving near-silent operation. The scientific block details harmonic coupling, phase-locked feedback, and over 95% acoustic cancellation. This phase enables stealth propulsion and nonlinear field amplification, further enhancing the craft's operational envelope. Narration 9 unlocks agile omnidirectional propulsion through gravetic lens arrays and directional field steering. Toroidal and parabolic lens structures focus gravetic fields into beams, while radial modulator arrays control vector orientation. Shell-integrated refraction channels maintain field coherence, and AI-driven feedback ensures precise maneuvering. The scientific block covers lens refraction efficiency, multi-lens synchronization, and rapid vector shifts. This phase replaces mechanical control surfaces with field modulation, enabling advanced flight profiles. Narration 10 integrates shell-embedded sensor arrays and distributed AI cores for full environmental awareness and autonomous flight intelligence. Multimodal data fusion aggregates pressure, temperature, ion density, and magnetic flux inputs into unified situational models. AI navigation algorithms predict flight paths and adapt to turbulence, while self-correcting modulation loops maintain stability. Redundant decision nodes and failsafe protocols ensure mission reliability. The scientific block highlights rapid decision latency, high hover precision, and consensus-based safety. Narration 11 introduces gravetic cloaking, field obfuscation, and signature suppression. The craft's shell is equipped with cloaking nodes, field obfuscation emitters, and diffraction nodes, all working together to form a stealth envelope. Energy flow arrows illustrate how phase-curved fields and ambient distortion suppress detection. The scientific block discusses dynamic field manipulation, silent signature damping, and resonance-based diffraction disruption. This phase enables silent propulsion and advanced stealth capabilities, even in complex electromagnetic environments. Narration 12 brings gravetic anchoring, hover stabilization, and terrain-locked flight. The craft features anchor nodes emitting downward beams, hover flux nodes for radial stabilization, and terrain-locked sensors interfacing with ground topology. Neon field overlays visualize hover bubbles and anchoring vectors. The scientific block covers terrain coupling, locked hover, and field overlays, ensuring stable terrain following flight even in challenging environments. This phase marks a leap in precision landing and stationary operations. With 12 generations complete, the AURIGAVIS hybrid lenticular aerospace craft stands as a testament to continuous innovation. Each phase, from diamagnetic lift to quantum diagnostics, and from environmental coupling to autonomous intelligence, has contributed to a robust, modular, and stealth-capable aerospace platform. The archival sequence preserves every scientific theory, visual cutaway, and credited innovation, ensuring a clear lineage for future advancements. This evolutionary journey demonstrates the power of interdisciplinary engineering and scientific rigor. Lenticular shell's unique geometry is not just for aesthetics, it's a functional design that optimizes field distribution and structural integrity. Lightweight composite layering, including carbon fiber metacomposites and diamagnetic hybrids, ensures strength without excess mass. Internal density redistribution further reduces apparent weight under strong field gradients. This careful balance of materials and architecture is foundational to the craft's performance and efficiency. Subsystem compacting is a hallmark of the AURIGAVIS hybrid design. Miniaturized power conditioning units, integrated field gradient coils, and containerless processing chambers are all embedded within the shell. This approach reduces redundancy, maximizes available space, and allows for in-situ material tuning. The result is a highly modular and adaptable craft, capable of rapid upgrades and reconfiguration as new technologies emerge. Energy flow within the AURIGAVIS hybrid is meticulously mapped for efficiency and control. Field gradients initiate diamagnetic lift, which is then coupled with gravetic modules to produce net propulsion. Arrows throughout the visual cutaways trace these flows, providing a clear understanding of how energy is transformed and directed within the craft. This mapping is essential for diagnostics, optimization, and future enhancements. Embedded avionics and AI control cores are distributed in radial compartments within the shell. These systems manage navigation, propulsion modulation, and environmental sensing in real time. Cryogenic isolation chambers and superparamagnetic admixtures further enhance performance by shaping field gradients and maintaining system integrity. The integration of advanced avionics and AI is key to achieving autonomous, adaptive flight. Achieving the right balance between strength and weight is critical for aerospace applications. The AURIGAVIS hybrid employs reinforced metacomposites for structural strength, while hollow-core lattice structures reduce overall mass. This combination ensures the craft can withstand operational stresses without sacrificing agility or efficiency. The design philosophy prioritizes both durability and performance, setting a new standard in aerospace engineering. The AURIGAVIS hybrid poster series serves as both a visual archive and a technical record. Each generation's poster features a realistic cutaway, labeled subsystems, energy flow arrows, and a scientific theory block beneath. This format ensures that every innovation is documented with clarity and precision, providing a comprehensive reference for researchers, engineers, and future project contributors. Beneath each poster, detailed scientific theory blocks explain the principles, data, and postulations driving each generation's innovations. These blocks cover everything from quantum validation and electromagnetic losses to field modulation and gravetic diagnostics. By anchoring visual artifacts with rigorous theory, the series maintains archival integrity and supports ongoing research and development. Looking ahead, the integration of all these systems, propulsion, diagnostics, environmental coupling, and AI, positions the AURIGRAVIS hybrid as a leading platform for advanced aerospace research. Each generation's innovations are credited to Colonel James Edward Hartman, establishing a clear lineage and a foundation for future breakthroughs in gravetic and diamagnetic flight technology. One of the key strengths of the AURIGRAVIS hybrid is its modular architecture. Each subsystem can be upgraded or replaced as new materials and technologies become available. This flexibility ensures the craft remains at the forefront of aerospace innovation, capable of adapting to new scientific discoveries and mission requirements without a complete redesign. The craft's ability to adapt to changing environmental conditions is a major advantage. Real-time sensor feedback and AI-driven modulation allow the AURIGRAVIS hybrid to maintain optimal performance in varying atmospheric, electromagnetic, and gravitational environments. This adaptability is crucial for both terrestrial and extraterrestrial missions, ensuring reliability and safety across diverse operational scenarios. Stealth and security are integral to the AURIGRAVIS hybrid's design. Advanced field obfuscation, signature suppression, and cloaking technologies ensure the craft can operate undetected in sensitive environments. These features are not only valuable for defense applications, but also for scientific missions requiring minimal disturbance to their surroundings. Quantum diagnostics, as explored in Generation 4, provide a new frontier for validating gravetic effects. By using dual-mass interferometry and entangled mass arrays, the craft can detect non-local interactions and displacement mismatches that traditional sensors might miss. This capability opens up possibilities for fundamental physics research and advanced propulsion validation. Field shaping and control are at the heart of the AURIGRAVIS hybrid's maneuverability. Through gravetic lens arrays, vector modulation, and real-time feedback, the craft can achieve precise directional control without mechanical surfaces. This approach not only enhances agility, but also reduces maintenance and increases stealth by eliminating moving parts. Thermal and energy efficiency are critical for sustained operation. The use of cryogenic flow channels, phase change heat sinks, and bidirectional energy recovery ensures that the craft can operate at high power levels without overheating or wasting energy. These systems work together to maintain quantum stability and extend the operational lifespan of key components. With fully integrated AI and sensor fusion, the AURIGRAVIS hybrid is capable of executing autonomous mission profiles. From takeoff and navigation to landing and diagnostics, the craft can operate independently, adapting to new information and unexpected challenges in real time. This autonomy is a game-changer for both exploration and operational efficiency. AURIGRAVIS hybrid lenticular aerospace craft is more than a single vehicle. It's a platform for ongoing innovation. As new materials, propulsion concepts, and AI algorithms emerge, future generations will continue to push the boundaries of what's possible in aerospace engineering. The Archival poster series ensures that every breakthrough is documented, credited, and ready to inspire the next wave of scientific discovery.